Here's a simple rate law question. They give you some data and they ask you to determine the rate law and calculate the rate constant. Now if you look at this, this is the method of initial rates. And so you're going to have to interpret the trials and find those ones that are useful. This is not concentration versus time. So let's have a look at what they're doing. Comparing trials 1 versus 2, you can see that for some reason they chose to triple the concentration of A while leaving B constant. Did it triple the rate? In fact, it did. If you take this number and triple it, you will get that number. So this is a proportional effect. We right now know that this reaction is first ordered with respect to A. You'll get a proportional effect. Let's see if trials 2 versus 3 tells us anything. They're changing both. However, we do know that it's first order with respect to A. They doubled A, so it should double. So we can factor that in. It should go up to 2.6. Now, once it's at 2.6, they're also doubling B. And look at that, it doubled again. So when it doubles, that means that it's first order also with respect to B. We had to factor in the effect of A and then see the effect of B. So just consider this to be 2.6 and then look at B independently. Here's the answer. Oh, by the way, we still need to get the rate constant. And for that, we can take any trial. And now that we know rate equals K times A times B, we can pick any of the trials, plug in that data, solve for K. Okay, let's reread this to make sure you understand it. So we write down the generic form of the rate law, and we need to determine X and Y. Comparing experiments 1 and 2, when A is tripled, the rate is tripled. Therefore, the rate is first order with respect to A, just like we said, so we get a 1 there. And then here's how they do the factoring thing. So we'll say it one more time. As A and B are both doubled, the rate increases by 4 times. Factoring the fact that it gets doubled by A, it must also be doubled by B. That's a nice way of explaining. So for B, the exponent is also 1. Now that means rate equals A times K times A times B. Rearranging, we can say K equals the rate over A times B. Plug in both 1.5. Looks like they took trial 2 for some reason. And we get an answer. You should get the same answer for any of the trials. And if you had time on a test, I'd verify that. So that we get a rate constant of 0.0058 molar per minute. A nice thing about this is that you can, it's actually 1 over molar per minute. When you do this, if you write down the units, and here it is molar per minute divided by molar, cancel everything out just like you would mathematically, you can figure out the values for K. So K does have values, and you can determine what they are experimentally, or you can simply memorize them. This is a little bit about a sample problem for rate constants.